going to start the lecture on advanced reaction engineering. So, in our previous class we already have discussed about the catalyst deactivation. So, there are various type of catalyst deactivations. So, and various reasons for the catalyst deactivation. So, in industrial scales if we conduct any let us say any reaction. So, that is here you can see that the gas well. So, if you want to crack the gas well to product formations. So, A is that is the reactant that is converted into B, C, D, many products formation is there. So, with that coke formation is there, the catalyst would be deactivated during the reactions at a particular temperature. Let us say we are conducting the reactions and we are putting this catalyst inside of the reactors. So, for the cracking reactions in the FCC catalyst, FCC reactor, catalytic cracking reactor. So, there it has been observed that the catalyst deactivate due to the coke depositions over the surface of the catalyst. So, therefore, the overall rate of the reactions, conversions, everything that is going down with the increase or progress of the reactions, or if we increase the time. So, let us say if we want to see after 1 hour, 2 hour, 3 hours, with increase of the times it has been observed that the rate of the reactions that is downs and the conversions also that is going to decrease. So, here you can see in the x axis we are plotting conversions and catalyst activity as well as concentrations. Okay. And y axis we are plotting this, and x axis we are expressing the time. So, here you can see that conversions, that is initially that was very good, and then with the progress of the times the conversion gradually decrease. So, that is due to the activity of the catalyst, means that is catalyst deactivated due to the coke depositions over the surface of the catalyst. Therefore, the activity of the catalyst or catalytic activity gradually decrease. So, and the concentration of the reactants, that is initially that was down when conversion was very high, and then after a certain period of time when conversion going down, the unreacted reactant concentration that is gradually increased. So, that is not our desire or expectation. So, whenever we conduct any reactions in a packed bed reactors, fluidized bed reactors, or any straight through transport reactors or moving bed reactors, when catalytic cracking reactions we are going means conducting for that particular reaction. So, then these are the things we observe, means when time progress the catalyst deactivations is there. Therefore, what we have to do? We have to change the catalyst frequently, very frequently, and then we have to replace with the new catalyst, and that spent catalyst you have to send for regeneration systems or regeneration unit, and once that catalyst will be regenerated, then again send back to the reactor. So, therefore, it has some financial issue, or whenever catalyst is going to deactivate, if we change frequently for a particular reactions in a when we are charging catalyst inside of the bed. So, that bed temperature or reaction temperature you have to increase, and or particular temperature that you have to maintain. So, when frequently we are going to change the catalyst deactivation is there. So, that is very common. So, when this deactivation process is there. So, let us say 0 hour to 24 hours if we conduct the reactions. So, with the progress of the reactions or increasing the times, the conversions gradually decrease. So, if we want to get the same conversions, let us say at the beginning 60% conversions was there, and after 24 hours here conversions you can see the conversion is very low, but again also we want to get conversion the 60% conversions within that time. So, if we conduct the reaction, so if we want to get the same conversions throughout the time, so then we have to change some parameters when the reactions we are conducting, that is the temperature parameters. So, with time, means with time conversion changes. So, we are conducting the reactions, let us say reactions a particular reactions we can conduct 500 to 700 or 800 degrees centigrade. So, at the beginnings we can conduct the reactions at very low temperature, and then catalyst deactivations would be there. So, at the same times conversions or product yield rates everything will be down. So, then how we can maintain the same conversions? So, why same conversion is required or same rate of productions or productivity? so for a particular product. So, it is required in a industrial scales whenever we are conducting a process or doing the reactions or systems running. So, then not only the reactors or a particular process we are operating, with that associated other process are there. With that means in a reactors we conducting the reactions, we are getting particular product, that products not only the pure products, with that some unreacted reactants, other byproducts, everything should be theirs, that we have to send to the distillations for separations that particular components, and after distillations units or distillation or separations process we can get the finals pure products. So, therefore, once catalyst going to deactivate for a particular system, so then the overall rate of productions, product yields, everything will be down, that would affect to the next process. So, in the separations process. So, therefore, to run or keep run everything when a system is running, let us say for 24 hours. So, then we can, if we want to get the same conversions throughout the 24 hours, catalyst deactivations is there. In spite of that, if we want to get the same conversions throughout the process, so then what we have to do, then we have to know the temperature time trajectories. Okay, that is the with in means there is some solutions, means how we can maintain the same conversions, that things we will discuss today. Okay. So, how the temperature of the catalyst reactor should be increased with times in order for the reactions rate to remain constant, means constant reactions rate, if you are able to get, if you want to get the constant reaction rate, constant conversions throughout the time. So, then temperature we have to, for that particular systems we have to increase with time. So, how means what temperatures we should increase at a particular times, at what rate the temperature we should increase for that particular systems, as if we can get the same reactions rate throughout. So, then we will get the same conversions, means loss of catalytic may be various types that we have discussed. Now, here is the catalytic activity. So, I said in a particular catalyst, if we conduct a particular reactions, it has been observed that slowly catalyst, the poisons of the catalyst, coke depositions, sinterings, these are the various type of catalyst deactivations we have discussed. So, in usually the poisons, due to the poisons, the catalyst deactivation, that process is very slow, not very fast. So, when means poisons molecule concentration is very low, that progressive gradually that is deactivating the catalyst, but that rate of the deactivations is very slow. So, when that slow deactivations is there, with the slow decrease of conversions or slow rate of reactions is slowly decreased. So, in that case, when slow decay is there, then temperature trajectories that we have to use. So, what is temperature time trajectories, that I will discuss, and if moderate decay is there, then some these temperature trajectories we do not have to use, then moving bed reactors we can use. If catalyst deactivate very rapid, means coke deposition, sinterings very fast is there. So, in that case we have to use straight through transport reactors. So, this is for rapid deactivations, moderate deactivations, slow decay or slow deactivations of the catalyst. So, for the slow deactivations, this temperature time trajectories is very useful. Okay. So, what is this temperature time trajectories, that we will discuss. So, catalyst decay for this particular process, when the process of systems is very slow, catalytic decay is relatively slow, in that case we can use the temperature time trajectories. Okay. So, here I said we need constant conversions when catalyst is deactivating. See here, this is our reactor system, fluidized bed reactor, let us say. So, here this is the feed stream that we are feeding at a particular temperature, and this is the preheater. So, here feed temperatures we increase with the help of preheaters, that preheater we have to connect before entering that feed streams into the reactors. This is a reactor, fluidized bed reactor, let us say. Here reactants plus catalyst both will enter, and here reactions will take place, and then product streams will leaving from here. So, here the feed streams whatever we are increasing at that temperatures we can fixed or make, we can increase or gradually increase this temperature. So, here this temperature time trajectories purpose is that with increasing times, let us say we have to conduct a reactions for 24 hours. So, gradually or slowly we can increase the feed temperatures. So, T0 to T temperature, T means at any temperature, T0 initially let us say it was 350 degrees centigrade it was, but here with the preheaters it is changing the temperature maybe 360, 370 like that, we can progressively we can increase, and that heated stream we can feed here, means reactions earlier let us say we are conducting the reactions at 350 or 360 degrees centigrade. So, with progress of the times catalyst will be deactivated, at the same times we are increasing the temperature of that particular system. So, as if we can get the same rate, constant rate, okay, constant rate for the catalyst. So, here left hand side you can see when t equals to T0 at small t, that is the time initially, that time that temperature was T0, that at that particular temperature we are conducting the reactions. So, when minus R A equals to R A prime equals to T and T capital this T. So, here at a time means here initially to at any times this time rate, this is initial rate, this is at a time t rate. Here we have maintained the temperature that was initially or beginning for that particular reaction was T0, but here we are maintaining some different temperature, not T exactly T0 we are not using, we are maintaining temperature T. This T0 and T not are the same. So, this may be higher temperature. So, this may be 350 degrees centigrade and this may be higher than that temperatures, this greater than that this temperature. So, that may be 360, 370, 380, 400 degrees centigrade this T may be. So, that we have to means in this study we will discuss about how gradually the temperature let us say up to 400 we have to reach, means initially you have started this temperature and this is the final temperature. So, how gradually the rate of the temperature increase will be there with time progress of the reactions, since catalyst deactivation is there. So, this way we can maintain and the same rate, means initial rate and final rate with catalyst deactivation we can maintain, but by changing the temperature of the reactions. Okay. So, here let us say for the first order reactions, if we consider a reaction is a first order reactions. So, this is the rate we can write this way K naught T0 into Ca, that way we can write a rate constant at time temperature T0 and C is the concentrations, and in the right hand side you can see this is activity and this is the rate at temperature T. Okay. So, this activity and this is the rate at temperature T. So, that we can write K T, that is the reaction rate constant at this particular temperature, and this is the concentrations of that particular reactions. Reaction concentration we are not changing, only the reaction temperature will vary with the progress of the time. Okay. So, then these equations we can write. So, here we are eliminating Ca part from left hand side and right hand side, then these equations will be this. Okay. So, here left hand side is the K naught and right hand side K T into A T is there. Okay. So, here these equations we can write this here K T we can write as a function, this is the Arrhenius equations you can know. So, K T we can write K 0 E A by R into 1 by T naught minus 1 by T A. So, T 0 that is the initial temperatures and T is the at any temperature we are conducting the reactions. So, at that particular temperatures the reactions rate constant or specific reaction rate we know using this, and that activity term is also there at that particular temperature and time. Okay. So, now K naught we are eliminating from left and right hand side, and then we are rearranging these equations in this way. Okay. So, we can write this equation this way. See this equation, this K naught part we are eliminating, then this part is left and this part is left. So, this we are rearranging. So, if you rearrange it would come this after taking ln. If you take ln, so then this part would come out, and then we if you rearrange, then this is for reactions 1 upon T equals to gas constant, activation energy for that particular reactions, activity, and this is the initial temperature that we can write. Okay. So, this is for reactions. Okay. So, now catalyst deactivations or decay rate law that we can write, that already you have studied. So, R D equals to we can write minus dA by dt equals to K D into A to the power n. So, we do not know what would be the order of the decay. the n may be 1, 2, 0.5, any numbers. So, then for this catalyst decay rate law we can write this way. So, this we can write this way, Kd we can express in terms of similarly Arrhenius rate constants or Arrhenius equations that we have expressed for the reactions rate constant. So, this reaction rate constant we have expressed this way in terms of activation energy and temperature. Similarly, catalyst deactivation rate constant or Kd we can write this way in terms of the temperature and deactivations activation energy for the catalyst deactivation energy. Okay. E is the activation energy for the main reactions and Ed is the activation energy for the catalyst decay. So, both are different. Okay. So, here K d naught is the decay rate constant at temperature T0. Okay. So, this way you can write equation 5. So, now here the temp 1 by T whatever we have get from the main reaction that we are substituting here. Okay. This part we are substituting here. So, once we substitute it here, so then it would be this. So, E d by R is remaining there, 1 upon T 0 is there, just one this part we are substituting here, 1 upon T naught, 1 upon T naught that would be eliminated and only this part would remain here, and then R part would be eliminated and only activation energy for the reactions and activation energy for catalyst deactivation that remained over there. So, then minus dA by dt we can write this way, minus dA by dt equals to Kd 0 and activation energy for deactivation, activation energy for reactions ln A and this A to the power n. So, these equations also again we rearrange and so we can get this way. Okay. So, this is this way you can write these equations. Now, after rearranging these equations and if we integrate A equals to 1 at t equals to 0 and under this case n minus E d by E a not equals to 1. Okay. So, in this case if we integrate this, so finally we will get these equations. This equation is time, activation energy for catalyst deactivations, activation energy for the main reactions, and this is n. N is the this is the order for catalyst deactivation I said. So, here this is the n is the order of the catalyst deactivations. So, this part is coming. So, here left hand side is the time and right hand side we are expressing in terms of activation energy for main reactions, at the same time catalyst deactivations E d. Okay. So, now substitute this means here A components is there, equation 3 we have discussed here. So, this part we have discussed, equation 3 is there. Here activity in terms of if we take it here and this part if we to left hand side, then this equation should be this equation 3, this K 0 part we can eliminate, activity terms is there, this part we are substituting here. So, after that if you simplify here this equation, then it would come this way. Okay. So, this equation by step we are eliminating all the unknown components and activity terms we are eliminating or substituting in terms of the temperature and activation energy. So, then equations would come like this. So, these equations actually is the temperature and time. So, here this is the temperature and this is the time, this part, and rest of the parts are the activation energy for the reactions, activation energy for the deactivations, and n that is the deactivations order if we know, and this is the T 0 is the initial temperature, T 0 that is the initial temperature or beginning of the reactions that we have started with. So, if we put all components or parameter in the right hand side of the equations 8. So, then we will get temperature and time. So, 0, 5, 20, 30, 60 like that. If we increase let us say in minutes times and corresponding temperatures, this T would come, this T is here. Okay. So, T 0 means for a particular cracking reactions at the beginning, let us say it is going to started with 500 degrees centigrades. So, y axis we are plotting temperatures, x axis time. So, here initially 500 degrees centigrade would be there, and after that 5 minutes if t equals to 5. So, then what would be this temperature? So, that may be 5 degrees centigrade, at 20 minutes may be 500 at 10 degrees centigrade, like that. So, if we get this value or this table from these equations, equation 8. So, if we plot temperature against time, so then the nature of the curve should be like this. So, it indicates actually how the temperature of the catalytic reactor should be increased with time in order for the reactions rate to remain constant. Here reactions conversions, here conversions, both places should be the same, this place and this place, let us say the conversions, only the changes is the temperature of the reactors for that particular cracking reactions with progress of the time. If we increase the time of the progress of the time, means from now to 24 hours. So, if we want to see that particular reactions, catalyst deactivations is there, since catalyst is means here the study what we are doing, that may be catalyst poisoning, catalyst deactivation is slow, but their deactivations is there. So, with progress of the times means now and after 24 hours, the conversions rate would be different due to the deactivations of the catalyst active sites due to the poisons. So, therefore, if we want to maintain the same reactions rate, same conversions for the process, so then we have to increase the temperature of the reactor slowly, not suddenly jump we cannot do, means slowly, means up to let us say 24 hours. After that catalyst maybe will be deactivate, very catalyst will be deactivate, but the rate and conversions remain the same by increasing the temperatures. So, this will actually tell us means how we increase the temperature of the systems to get the same conversions of the reactants and same rate of the reactions. So, this will tell us. So, now here's let us say n is the one we are putting here in that equations we have developed, this equation 8 we have developed. So, now in these equations if we consider that for assumptions the catalyst decay rate that is following first order. Okay. So, n equals to 1 if we put in this equations, n equals to 1 if we put. So, then this equation should becomes this. Okay. So, this is for first order reactions, okay, first order decay rate, but reactions rate we do not know, but reactions decay rate law that was nth order, that may be any order. So, here for examples if we consider a first order decay rate for that catalyst deactivations process. So, then time and temperatures how they are related, it is very much more simplified equations is coming. Okay. So, here see here in the right hand side temperatures and time, this is called temperature time trajectories. Okay. So, temperature how they are related with the time. So, how will increase the reaction temperature for that systems as you maintain the same rate of conversion. So, here's if you notice the temperature time trajectories for this particular catalyst deactivation process, here some model has been shown, here's run 1 and run 2. So, that you can see it here, means by using this equation for n equals to 1 and n equals to 1 means first order catalyst deactivation process. Let us say run once we have conducting the particular cracking reactions at a particular temperatures, let us say 740 degree Fahrenheit we have started the reactions. Here x axis time is progressing 100, 200, 300, 300 time hours. Okay. So, whence this is 0 hour means at the beginning we have started with this, the temperature of the reactor was this. So, if we 100 hours if we look into this, here the temperature is slightly increased, 3 hours 200 hours reactor temperatures increase to this, at 300 hours reactor temperature is increased to this. So, for run once or experiment once, the temperature gradually you have to progress this way, that way we have to with changes of the times the temperature of the systems or the reactors we have to gradually slowly increase. Okay. So, this is the way. So, at these times what temperature we should maintain, at these times what temperature we should maintain, that is from these equations we easily find out. Okay. That correlations we can this from these correlations we can find out the exact times and exact temperature that we have to maintain to get the same reactions rate and for same conversions, but catalyst deactivations is there. Similarly, run 2 also you can see, if we start let us say 508 we have started the reactions, and so with progress of the times the catalyst deactivations is there. So, the way we have to run the systems or increase the temperature of the systems or the reactors this way. Okay. So, here you can see let us say this run 1, here this is the activation energy for the reactions, and here catalyst deactivations activation energy is this much. This is the some experimental results from one particular cracking of gas wells or crude oil. So, that has been studied for a particular system and catalyst deactivations was theirs, and in that particular systems based on experimental data that modeling was done, and based on that it has been observed that run 1 and run 2 the activation energy remain the same for the same reactions. Reactions if we want to conduct a particular temperatures, so then rate activation energy is very important. So, that particular activation energy, that particular rate or particular conversions will get, but here you can see decay activation energy catalyst deactivations at this temperatures when it was started, this deactivation energy or catalyst decayed activation energy was this, and for this run 2 catalyst deactivations rate was this. Okay. So, here in this case it has been observed and said that means at the beginning a few hours that coking or fouling of the acidic side should be there. So, then it has been initial the this divided this temperature and time trajectories, that is divided into 3 regime. Okay. So, this temperature time trajectory has been divided into 3 regime. So, initial that is the coking or fouling of acidic sides of the catalyst, and then linear regions that is due to the slow coking this part actually up to this that is due to the fouling of the acidic sides. In the acidic side solid as catalyst is there when cracking reactions is there. So, in that catalyst there are number of acidic sites, basic sites are there with the active sites. So, that active sites will be a coking or fouling whatever that is going on inside of the catalyst or surface of the catalyst. In at the first beginnings it has been observed that acidic sites of the catalyst that is blocked. Okay. And then second part is or region, that is the linear region is there slow coking is there, slowly coking or coke formation is there, that is deposited over the surface. And then third is accelerated coking, means here very fast you can see the temperature time trajectories, here the slowly changes, here also slowly changes, here accelerated changes are there. Okay. So, therefore, this accelerated or exponentially increase of the temperature you have to maintain these regions. Okay. Here coking or coke formation would be very fast. So, their temperature here gradually or jumping or rate of the increase of the temperature would be very high, means at the beginning since the catalyst deactivation is very slow, therefore, slowly we have to increase the temperature, but with progress of the reactions if we go for up to this time, then we have to let us say initially 5 degree per minute we have to increase, but here let us say catalyst deactivation is very fast or accelerated coking is there. So, here maybe 20 degree centigrade per minute, that way we have to increase the temperature in the catalyst beds. So, that way means that analysis was done based on one experiment that was conducted and to understand about the temperature and time trajectories, and based on that they have developed some models, and in that models and experimental result, this is basically the model theory and experiment, means from the experimental data they have model and fitted with the experimental observations, and that model was fitted very well. So, here this lines and here this line is the theory, and these points or circle points you can see over the line, that is experimental data points. So, both was validated and this model was developed. Okay. That is very means experimental results and the model predicted means matching very well. So, therefore, this model is acceptable and this model is studied or we are discussing here, that is why. So, here this is called temperature time trajectories, means how when catalyst deactivation is there. So, with progress of the time or progress of the reactions with increasing times, how will increase the temperature of the systems or to maintain the same conversion or same reactions rate for the process. Okay. So, today is up to this. So, I think the you understand about the temperature time trajectories, what is called and why it is important. Okay. So, for catalyst deactivations process. So, today is up to this. Okay. Next class we will discuss some other reactors. So, okay. Thank you.